Hello everyone, I am Sunil Kumar from EML department and I am going to present the experiment 3 and where in which I will explain the program line by line and how it works. First, import NumPy as NP where it imports the NumPy library under the alias MP which is commonly used for array manipulation and mathematical operation. Next line where import pandas as PD where imports the pandas library under the alias PD, which is commonly used for data manipulation and analysis. Next line is import IO, where import the IO module, the which provides Python's main facility for dealing with various types of IO operations. Next is import matplotlib.pyplot as PLT, where it imports the pyplot module from matplotlib library under the alias PLT, which is used for creating and visualization. And, and after importing these all modules, we are going to initialize the input vector and output vector for XOR operation, where we are going to create two variables x and y, where x contains np.array of input vectors x and y equal to mp.array where output vector as y in x equal to mp.array of 0, 0, 1, 1 and 0, 1, 0, 1 where it initializes the input vector x as numpy array with shape 2, 4. Each column of x represents an input sample for XOR operation in y equal to np.array. It initializes the output vector y as a empty array with shape 1, 4 and a single row contains the expected output for each corresponding input samples. And next we can see the number of neurons in input layer, hidden layer and output layer. We are going to create three variables n underscore x, n underscore y, n underscore h, where n underscore x denotes the number of neurons in input layer and n underscore y denotes the number of neurons in output layer and n underscore h denotes the number of neurons in the hidden layer. Next, we are going to create a variable m equal to x dot shape of I, where it denotes the number of training example, which is number of columns in an input matrix X. And we are going to create a learning rate equal to 0.1, and we are going to set the random seed to two for reproducibility, where w equal to np dot random dot rand of n underscore h comma n underscore x for weight matrix for hidden layer and w2 equal to np dot random dot rand of n underscore y and underscore y n underscore h for weight matrix for output layer. And next we can see the losses equal to a empty array. This code defines the this function forward underscore prop that performs forward propagation in neural network with two layers. Here step-by-step explanation of code. Sigmoid z is a function that computes the sigmoid activation function for given input z. The sigmoid function is commonly used in a neural network to introduce non-linearity. Forward underscore prop function that takes three arguments w1, w2 and x. w1 is for wait for first layer, w2 is wait for second layer, x is input data. Inside forward underscore prop x is z1 is computed as dot product of w1 and x. a1 is computed as sigmoid of z1, z2 is computed as dot product of w2 and a1. A2 is computed as sigmoid of Z2. This function returns Z1, A1, Z2, A2. In the next, we are going to see about the back underscore prop, back propagation that performs back propagation by neural network with two layers. Here step-by-step explanation of the code. Back underscore prop has three or takes eight arguments where m, w1, w2, z1, a1, z2, a2, y. M is a number of tiny examples. W1 and W2 are weights of the first and second layer respectively. Z1 and Z2 are pre-activation value for the first and second layer respectively. A1, A2 are the activation value for the first and second layer respectively. Y is the ground truth or actual input or output. Inside back underscore prop, it contains bz2 equal to a2 minus y, where it is computed as the difference between the predicted output a2 and the actual output y. In dw2, we have computed as the dot product of dz2 and transpose of a1 and divided by m, and dz1 is computed as the dot product of transpose of w2 and dz2 multiplied element wise by derivative of sigmoid function applied to a1, and then d1 is computed as the dot product of the d1 and transpose of the input x divided by m. The shape of d1 and d2 is reshaped to match the shapes of w1 w2 respectively. The function d1 and dz1 dz2 and dz3, which are gradient used to update the weights during the optimization process. Next, we are going to see about this slide iteration people iteration. The the for the loop runs for iteration and performs following each iteration. Computes the forward propagation to get the predicted output A2. Calculates the loss using the cross entropy loss function. Appends the loss value to the loss list. Computes the gradient using backpropagation. Updates the weight W1 and W2 using gradients and the learning rate LR. After training, the code plots the loss list to visualize how the loss value changes over epochs, the iterations. And then this code defines the and then this code this code defines the prediction defines a function predict that use the trained weights W1 and W2 to make prediction for the given input.